Hello, today we're going to do a titration of vinegar, just from a bottle from the grocery store, and sodium hydroxide. And this lab could be done with Unit 4, where titrations are introduced, and they're kind of introduced to the different types of chemical reactions, including acid-base reactions. Or you could do this with Unit 8. Now, or you could do it both. You could apply different concepts here. This one in particular is using the titration with an indicator, and the goal is to find the concentration of the acid in the vinegar solution. Later on, we will do another titration where we use a pH meter and explore titration curves. That one we definitely do with Unit 8. But this is a nice introductory lab to titrations. Another way that you could do this lab is having the students bring in different fruit juices or soft drinks, and then they can test their own sample. I just happen to have vinegar handy today, so that's what we're going to be testing. Keep in mind that if you're using other substances, that there might be different numbers of hydrogens that are acidic, like citric acid has 3 acidic hydrogens. Phosphoric acid, which is present in a lot of sodas, also has 3 acidic hydrogens. So just keep in mind that some of your calculations might be a little bit different based on the type of acid that's present in the solutions that you're testing. So what I'm going to do is I'm going to use 25 milliliters of the vinegar, and I'm going to use a graduated cylinder to measure this. If you have a volumetric pipette that measures 25, that would be a little bit more accurate. You could even use a burette, another burette, to transfer more exactly 25 milliliters. This is a great time to talk about the precision of your measurement tools. Graduated cylinder is what I have handy and easy to use, so I'm going to use that and transfer that into my Erlenmeyer flask. And then I'm going to use an indicator. I will use phenolphthalein for this one. It changes color around a pH between 8 and 10, so it's pretty good for a weak acid, strong base titration like this. I'll use 2 to 3 drops. And then I will place that on the hot plate stirrer. Remember not to use the heat, just the stir part. And I will turn on the stir function nice and low, so that way it doesn't splash up. Don't forget to have students adequately prepare the burette before starting. So you want to wash the burette with deionized water first. Then rinse the burette with the titrant to push out any excess water. Make sure that the titrant completely fills the tip of the burette, and then you can fill the burette. It doesn't have to be completely full up to the 0 line. You can start it somewhere in the middle, as long as students record the starting amount and then the final amount from the burette reading. They should be good. You could also, if you don't have burettes, you could also do this lab using mass. You could, or even like a graduated cylinder, honestly. You could have students measure the masses before and after. So like you could have a container of sodium hydroxide titrant, record the initial mass, use a transfer pipette, and just add drops into your Erlenmeyer flask until it turns color with the indicator, and then use the change in mass and the density of sodium hydroxide to figure out how many moles it took to. So I'm going to go ahead and titrate this until we reach a faint pink color, and then we'll stop. Now once it reaches that light pink, pale pink color, students should stop titrating and record the final volume from their burette. And then I usually have students, sometimes we'll do multiple trials depending on the amount of time we have. Sometimes we'll do, each group will do a trial, and then we'll compare and calculate like a class average. But typically I will have students start to clean up as we're waiting for all of the groups to finish before we move on to calculations. All right, so let's look at the calculations for this lab. The sodium hydroxide titrant that we used was 0.623 molar, and it took 33.80 milliliters of that to reach that pale pink color, to reach our endpoint. Now, our original vinegar solution, we had 25 milliliters of that stuff, and it reacts according to these equations. So this is the full balanced equation, sodium hydroxide reacting with acetic acid to form sodium acetate and water. But the sodium ion is a spectator ion. So it's a good time to point out that strong bases and acids will completely dissociate, but weak ones will not. So when the sodium hydroxide completely dissociates, the sodium acetate completely dissociates, and so the sodium ion is a spectator ion. This is important to talk about because this is a one-to-one reaction here. If you are doing a different substance like citric acid or phosphoric acid, you might not have that one-to-one relationship. So you should definitely balance the equation ahead of time. So then to calculate, we're trying to find our molarity of the acetic acid as the goal for this lab. Okay. So what I need to do is first find the moles of sodium hydroxide that it took to titrate. You will take the milliliters, convert that to liters, 0.03380 liters, times the molarity will give us moles. So 0.0211 moles of sodium hydroxide. That means we had 0.0211 moles of hydroxide ions because it completely dissociates. And since it's a one-to-one relationship, we also had 0.0211 moles of acetic acid. Now that we have our moles of acetic acid, we can find the molarity of acetic acid. We have 0.0211 moles and divided by the liters. Remember, we had 25 milliliters, so 0.0250 liters, and divide to find the molarity. We've got 0.842 molar for our final answer. Now, students can then find a class average if they're all doing the same solution, or if they're doing different substances, like if they're doing different fruit juices or soft drinks, they could rank the concentration of acid and create a list, and that's what I'll do sometimes. And it's really interesting to see how some things might contain a greater concentration of acid than others, and it might be surprising some of the different substances. You should also talk about sources of error, like the fact that your end point, which was the 33.8 milliliters of sodium hydroxide, that end point necessarily must be past the equivalence point. In order for the solution to change color, it must have extra sodium hydroxide to react with the indicator. So the end point is always just a little bit past the equivalence point. So that's a little bit of a source of error. So you have a slightly higher volume than expected, which means that you have a slightly higher number of moles and a slightly higher molarity calculated than would be the really true value. Other source of error might be if they didn't prepare the burette properly and there was water left over in the burette, that would decrease the concentration of the sodium hydroxide used. So it would take more volume of our base to react than you really should have needed. And so that would mean our moles was too high and then our molarity was much higher than the true value. So always talk about those sources of error because they pop up on the AP exam quite frequently.